So this is the change in cosine over the change in time. If I look at the slope of this, well, I've got 0 here and here. It is a negative slope, positive, negative. What's the slope of a negative sine curve?
Negative cosine.
This is the change in negative sines, or the change in time. The slope of a negative cosine. So it's 0 here, here, and here, and it's positive, and then negative. And the slope of sine, and then we cycle back to the top. Don't worry, more than just random facts. What is the relationship between charge and current? Just had a test on it.
C equals Q over V.
Looking charge and current. What's the definition of current?
V equals IR.
That's an offshoot of it. Definition of current.
Charge over time.
Yeah, roughly. What we did before is that current is the change in charge over the change in time. It's how much charge passes by at a particular amount of time. Since we're dealing with AC, I is equal to change in Q over change in time. In other words, my current here should just be the slope of this. And so what is the slope of this?
Negative sign.
So negative C epsilon omega sine of omega t. So if I plotted So if I plotted the voltage is looking like this. That's my voltage. My current is a negative sign, so it's looking like that. This is my current. Notice that one is in front of the other. Time progresses. This is basically time out this way. This is the time axis. Not really fast. So as you're progressing in time, current comes just before the voltage curve. In other words, for a capacitor, current, I, comes before voltage or the EMF. In other words, when you're dealing with the capacitor, I comes first. That's what the ice is. Or what I had before, if this latches on, I assume you're familiar with the I before E except after C. So I before E when talking about C. So on a phasor diagram for my circuit over here, I would have a phasor here that would represent the power supply and the voltage across the capacitor. These are labeled with capital letters, because again, it represents the magnitude. And the current across the capacitor leads by 90 degrees or pi over 2. And as long as we just have a capacitor in the circuit and nothing else, that those two will stay in sync, so as time progresses, they will go around together. So we can come up with specific values. So assuming that, let's say that the power supply is 10 volts cosine of 2 radians per second T, then so that'd be the voltage of the power supply. It would also be the voltage of the capacitor. Let's make the capacitance equal to, that have to be a realistic number, 3 farads. So my current for the capacitor is going to be negative 3 farads times 10 volts times 2 radians per second sine of omega t, of 2 radians per second t, which is negative 60, what are the units?
Farad volt radians per second.
Otherwise known as no, it's the whole thing. If you multiply it all together,
Amps.
yes, amperes. So an ampere is a farad volt radian per second. Now you can always not write radians if you don't want to. So therefore a unit of time, a second, would be a farad volt per ampere. Presumably this is not a unit of time we've done before. Sine of 2 radians per second. And so that's it from the analytic point of view. From a phasor point of view, it's just we have these two things and they're both spinning around at a rate of 2 radians per second. And they will be locked in this 90-degree angle. Emphasize that is a right angle there. They'll be locked in this 90-degree angle the entire time. Questions here? Let's add another component into it. The inductor. That's right. All this can go. Was there a sound of?
I burped.
Oh, okay. Thought you wanted me to stop erasing. However, presumably it got picked up there and immortalized.
Yay.
It's about think about throwing out a fake name just to blame Ben. Ben, come on, how did you be burping?
So they get for not being here.
All right, so now we get to the inductor. Now we did inductance very briefly, because inductors really have far more impact when you're dealing with AC. So first off, what is the symbol for inductance? Oh, yeah. I think I worded it wrong, but Sarah, you answered it correctly. That is an inductor. It has that self-inductance involved, the fact that as the current changes, it creates a back current to try to oppose the change in the electric flux through the coils. And so it now comes down to what is the voltage, we'll do it in terms of DC, the voltage across an inductor. And we did derive this, so appreciate this, checking their notes.
Is it negative usage not? Is that, I'm not sure.
What's the whole thing you're doing?
Has negative usage not, n squared a.
Oh, that's the inductance itself, looking for the voltage.
Oh, negative L,
That's the one.
times, change in the current voltage in second.
All right, so that's what we did before. Inductance itself, Janice started to do it. That formula was mu sub naught n squared 8 over L. Sorry, different L. L. Now, the actual construction of it is not particularly of importance right now. What we care about is this piece right here. The negative sign, we're just sort of hand wave away or justify it. We're going to gain something across the power supply, and then lose going across the inductor, or we'll lose going across the power supply, or gain going across here. It's going to be one or the other. But we're going to go through the similar process of the change in voltage across the power supply. These are lowercase v's. I guess we'll sort of emphasize the fact that it's a lowercase v, minus the change in the voltage across the inductor. Should be 0. Again, Kirchhoff's voltage loop, you end up back where you started. I erased this, let's put this one back. So this is epsilon, so the voltage epsilon cosine of omega t. So we have epsilon cosine of omega t equals L delta I over delta t. Oops, that should be against lowercase I there. Delta I over delta t is equal to epsilon over L. Writing is getting worse and worse. That's typical. Epsilon over L cosine omega t. So I equals in other words, the function, whatever I is, I know that its slope, this is a slope here, the slope is going to give me cosine. So what is I?
Sine.
Do it again?
It's gonna be a sine function.
It would be. Sine is what gives you a slope of cosine. So this is epsilon over L omega. Y omega appears on the bottom. Remember, when we do slopes, we multiply times whatever the coefficient of the time is. And so this is just the reverse process. Sine omega t. So if I look at our plot here, the voltage is a cosine curve. So that's my voltage. My current is a sine curve. So now notice this way that as I'm going from left to right, I hit the voltage before I hit the current. Matter of fact, the difference between these 2 points, the lag here is pi over 2. So for an inductor, voltage comes first, or the EMF. That's what this is. For the inductor, the EMF comes before the current. In a phasor diagram, I draw my first phasor. It's traditionally put it in the first quadrant, but again, doesn't have to be. This is the voltage across the power supply, which should be equal to voltage across the inductor. And my current phasor lags by 90 degrees. Where this is a right angle. Questions to hear before I start going overboard? Because we're about to get to the really good stuff.
If we don't come back, like if they go online for the rest of the semester, will you like email us grades or same kind of thing? Like we email you to ask for grade or?
Yeah, worst case is that happens. I really should start posting. It's set up for me to post grades. I just haven't actually stuck the grades in there. But if I'm gonna miss out on the delightful conversation that goes along with that, then I may as well post them. But is the grade particularly important? Isn't it really about the learning?
It's a little important.
Well,
It's a little important.
A little.
According to some, the grade represents how well you're learning.
Yeah, I keep believing that.
Yeah.
Can you explain the Eli thing real quick again?
All right, so in a phasor diagram, it's a question, you basically have a voltage phasor and a current phasor for each component. The voltage, and so it's a question, what is the relationship between the two? So for a capacitor, the current comes before the EMF, or the voltage, by 90 degrees. So we can write it out in more formal language, and apparently I got my space over here, and part of the tradition of getting farther away from Janice, apparently. So for a capacitor, current leads voltage by pi over 2, or 90 degrees, whichever way you want to write that. For an inductor, current lags voltage by pi over 2. And for a resistor, we started out there, current is in phase with voltage. And this is setting up for us to be able to start analyzing more complicated diagrams, which is what we're going to do in just a moment. All right. Questions up to here? Other questions up to here? All right. Then let's get to the more interesting circuits. AC power supply, resistor, capacitor, the RC series circuit. Now we'll set up the phasors, then I'll drop back and cover reactants and things like that. All right. So to analyze something like this, there is a way of doing it without doing phasor diagrams. Phasor diagrams is just one technique. Another technique does involve using imaginary complex numbers. I tend not to do that method, especially since I haven't done that method in a couple of decades. So physicists tend to do the phasor diagram, engineers tend to do the more analytic complex numbers. At least that's been my experience. So we start out with, in a series circuit, what is going to be true about looking at voltage and current, what is going to be true about a series circuit?
Current is the same.
Yes. So when I draw my phasor, first thing that is typically you want to do is you want to draw the thing that is common to as much as possible. So I'm going to draw my current phasor right here. This would be the current coming out of the power supply, which is the current across the resistor, which is the current across the capacitor. The current should be the same throughout the whole thing. Now, we have a resistor and a capacitor. For a resistor, what do you know about the phasor for voltage and the phasor for current for a resistor?
Voltage is the same.
In phase, probably better wording. So I'm going to draw my voltage across the resistor along the same line. They're in phase, which means they hang together. Now, how long I draw it is up to me. Typically, this first one I draw, I make long enough so that the second one I draw, not as long, but you can still see it. There's no reason why it is shorter other than the fact that I want it to be visible. So this is the voltage across the resistor. What about the voltage across the capacitor? What do you know about its phasor compared to the current across the capacitor?
It's going to be behind.
Yep. The voltage comes after. So this would be the voltage across the capacitor. And for artistic reasons, in just a second, I'm going to make it slightly smaller. For no particular reason other than I know what line I'm going to draw next. And now the voltage come from the power supply is the one thing I haven't drawn yet. So this is epsilon cosine omega t. I know whatever voltage I gain across here, I have to lose across those. In other words, the sum of the voltages across here, across the two components, has to equal up to the voltage here. So what I'm going to do is I'm going to add these two phasors. Now the way you add phasors is exactly the same way you add vectors, head to tail, or the rectangle method, whichever one you prefer. So I'm only adding two here. That's the voltage across the power supply. And so I wrote it as epsilon just out of habit. You could also write it as just the power supply. Because that's a right angle there, that's a right angle there. I have a rectangle. I know in this case, I'm not writing down a formula that's always true. I'm writing down a formula that's true for this case, that VR squared plus VC squared is equal to epsilon squared. And now we bring Ohm's law in. Questions up to here before I bring Ohm's law. This is the thing that I hesitated on. At what point do I bring this stuff in? We'll introduce it now. Questions about this? All right, Ohm's law. What is Ohm's law?
Is that V equals I?
That's the one. So across a resistor, that's equal to IR squared. So you do have some relative relationship between the size of VR and the size of I because it's related to R. For a capacitor, what do? Well, let's go back to our formula before that. V was across the capacitor, lowercase v, was negative epsilon c omega sine omega t. I think that's what we had before. It's going off of memory and quick derivations. Okay, there's a subtle nod there. That is what I had before. Okay. This right here is equal to the voltage across the capacitor. No, whoa. That's not what I had before. That was the current. So that is the current, so I across the capacitor is equal to epsilon c omega. I want to put this into some sort of form like Ohm's law. In other words, Ohm's law, for DC, we had delta V equals IR, that was Ohm's law. And I do want to point out, I didn't mention this earlier, when dealing with AC voltage, the delta, I actually don't know if I've ever seen the delta. It's dropped, it's still implied to be there, but just recognize you don't write delta typically for AC. So we are now at this stage right here. I want to get it into that form. Well, this epsilon here is my voltage, so I'm going to solve for that. So epsilon would be equal to IC over C omega, which is IC times 1 over, I guess, omega C. This is not officially Ohm's law, because I don't think Ohm dealt with this stuff, but we have it in that format where we have some voltage is equal to current times something. This right here is known as the capacitive reactance. And the symbol is X sub C. And so over here, we can now write V sub C as I X sub C squared. Is equal to epsilon squared. And the fact that the capacitive reactance is 1 over omega C, that's always true. That's not specific to this particular problem. Taking it that next step, I'm going to square things here. So this is I squared R squared plus I squared X sub C squared is equal to epsilon squared. I'm going to factor I squared out. So I have I squared times R squared plus X sub C squared is equal to epsilon squared. If I take the square root of both sides, I get epsilon is equal to I times the square root of R squared plus X sub C squared. I don't know what you're thinking. You're going, wow, that's just amazing. I wish they had a name for that. You're in luck. Again, going with this Ohm's law kind of vibe where V equals IR, or delta V equals IR, voltage is equal to current times something, we have this right here. And of course, they have a name for it. The symbol is Z, probably because they didn't use Z for anything else. This is not always, this formula is not always true. This is true. The value for this is always dependent upon the circuit that you're dealing with. This is known as the impedance. It is not pronounced impedance. It's impedance. So there are a number of these type problems where ultimately they say, what is the formula for impedance, or what is the value of the impedance? That's something along those lines. For an RC series circuit, there's a formula, but I would recommend you don't try to memorize every single combination of resistors, capacitors, inductors, series, parallel, and various combinations as such, and try to memorize every single kind of formula there. That would be, for me, torture. But if you do happen to have 2 weeks off and nothing better to do, instead of plugging in numbers here, which might be the wiser course, I want to do a parallel circuit just to go through before we break up, to go through how to do an analysis in a slightly different situation. And then presumably there will be just these absolutely fabulous videos talking about bringing inductors into it, and things you can watch again with the family. Over Thanksgiving, hey, I've got this video on inductance.
Never forget.
That's right. That and Pearl Harbor. Any questions on this before I erase it? It's just so exciting, your brain is just tiring out really quickly. All right, we have a parallel circuit here. I guess I'll draw it slightly more traditionally. There we go. Parallel circuit, I have some resistor and some capacitance. What is true about things in parallel?
They have the same voltage.
And so when we draw our phasor diagram, we do that. So I will start out drawing, since the thing that's common to what we have here. There's my voltage across the resistor, which is the voltage across the capacitor, which is the EMF.